Binary search. If there's one algorithm interviewers expect you to speak fluently, it's binary search. It's the litmus test for algorithmic rigor, pointer discipline, off by one control, and logarithmic thinking. This pattern mastery 100 staple shows up everywhere, from search problems to boundaries and monotonic checks. Let's lock it in using basics so your explanation and code are crisp and unbeatable. We're given a sorted array nums and an integer target. Return the index of target if found, otherwise return -1. Because the data is sorted, we can eliminate half the search space each step by comparing the middle element to the target. Binary search runs in O log n time and O1 space, way better than a linear scan. Key pitfalls: computing mid, updating left and right correctly, and using while left less than equals right to avoid infinite loops. We'll return as soon as nums mid equals target, else move the appropriate boundary. Plan: initialize left equals 0, right equals len nums -1. While left less than equals right, compute mid. If nums mid equals target, return mid. If it's smaller, discard the left half by doing left equals mid +1, otherwise discard the right half via right equals mid -1. If we exit the loop, return -1.
Let's try to implement it using solution 1. We begin by defining the solution class, the container for our method. Then we declare the search method, which receives a sorted array, nums, and the target value we want to locate. Next, we create two pointers. L starts at the left end of the array, R starts at the right end. These pointers mark the boundaries of our current search window. After that, we begin a binary search loop. We continue searching as long as the left pointer hasn't passed the right pointer. Because the window shrinks by half each time, this runs in O of log n. Inside the loop, we compute the midpoint m. This is where we check first, similar to flipping to the middle page of a book to decide which direction to explore. Next, we check if the value at index m matches our target. If it does, we return the index immediately. The search is complete. Otherwise, if the midpoint value is less than the target, that means the target must be to the right of m. So we move the left pointer forward. And if the midpoint value is greater than the target must be in the left half. So we move the right pointer backward. This closes the binary search loop. By now, our search window has either found the target or narrowed down to nothing. And finally, if the loop ends without finding the target, we return -1. That indicates the value is not present in the array. And that's how this algorithm works. It first sets up left and right boundaries. Then it checks the midpoint and shrinks the search window based on comparisons. It repeats this process until the target is found, or the range collapses. Efficient, simple, and elegant. Check. This test verifies the binary search implementation on a sorted array. The input array contains -1, 0, 3, 5, 9, and 12. The target value is 9. Because the array is strictly increasing, it fits the binary search requirement. The goal is to return the index where the target appears. If we list the values with their indexes, index 0 is -1, index 1 is 0, index 2 is 3, index 3 is 5, index 4 is 9, index 5 is 12, so the value 9 is at index 4. During binary search, the algorithm narrows the range until it lands on nums at index 4 equals 9. That confirms the correct index. The output is 4. Matching the expected 4. The search logic correctly identifies the position of the target value in the sorted array. Now let's try another implement approach using solution 2. We begin by defining the solution class. This class holds both the public search method and a private recursive helper. Then we declare the search method. It receives the sorted array and the value we are looking for. Next, instead of doing the search directly here, we delegate the work to a recursive helper method. We pass in the array, the target value, and the full search boundaries, from index 0 to the end of the array. Now we enter the recursive helper. This method receives the array, the target, and the current search window defined by the left and right pointers. First, we check the base case. If the left pointer moves past the right pointer, the target is not in this range, so we return -1. Next, we compute the midpoint of the current range. This is the position we inspect first. Similar to opening a book to the middle page to decide which direction to go. Then we check whether the midpoint already contains the target value. If it does, we immediately return the index. The search is complete. Otherwise, if the midpoint value is smaller than the target must be in the right half of the range. so we recursively search from the position just after the midpoint to the right boundary. And if the midpoint value is greater than the target must be in the left half, so we recursively search from the left boundary to just before the midpoint. And that's how this algorithm works. It starts by passing the full range into a recursive helper. Then it repeatedly splits the search space in half. At each step, it chooses the left or right side based on the midpoint comparison. This continues until the value is found or the range becomes empty. Efficient, simple, and elegant. Check. This test verifies binary search behavior when the target does not appear in the array. The input array contains -1, 0, 3, 5, 9, and 12. The target value is 2. Because the array is sorted, binary search can efficiently narrow the search space. The value 2 does not match any element in the list. It falls between 0 and 3. But since neither value equals 2, the algorithm continues shrinking the range. During the search, the algorithm compares the midpoint, then redirects to the appropriate half based on ordering. This continues until the search space becomes empty. At that point, the algorithm concludes that the target is not present, so the correct return value is -1. The output is -1, matching the expected result. This confirms the solution correctly reports when the target is absent from the sorted array.
Let's have a quick recap. Breakdown recap. So, to wrap it up, binary search is all about finding a target efficiently in a sorted list. Instead of checking one element at a time, we cut the search space in half with every step, comparing the middle element to the target. Assess recap. We compared approaches and saw why this one stands out. A linear scan takes O(n) time, but binary search drops it to O log n. The key challenges aren't in the math, they're in managing pointers, avoiding infinite loops, and computing the mid correctly. Structure recap. The logic was straightforward. Set 2 pointers at the start and end, find the middle, and adjust the search window based on whether the target is smaller or larger. Keep narrowing until it's found or the window closes. Implement recap. When we implemented it, everything came together through a clean loop that halved the range at each step. The left and right pointers guided the search precisely, and returning the mid when found kept the function minimal and robust. Check recap. We ran multiple test cases, finding numbers correctly and returning -1 when not found. Every run matched expectations, confirming our binary search logic worked perfectly in logarithmic time. The big takeaway? Binary search isn't just a single algorithm, it's a mindset. Mastering it trains you to think in halves, control boundaries precisely, and reason with mathematical efficiency, skills that show true algorithmic discipline in any coding interview.